students, and welcome to the lecture on error detection and correction. After the lecture, we will be able to learn the following objectives. Describe the types of errors and error detection. Discuss block coding. Explain error correction. Describe the Hamming distance. Explain linear block codes. Understand the simple parity check code. Let's start with a brief introduction to error detection and correction. Networks must be able to transfer data from one device to another with acceptable accuracy. For most applications, a system must guarantee that the data received is identical to the data transmitted. Anytime data is transmitted from one node to the next, it can become corrupted in passage. Many factors can alter one or more bits of a message. Some applications require a mechanism for detecting and correcting errors. Data can be corrupted during transmission. Some applications require that errors be detected and corrected. Some applications can tolerate a small level of error. For example, random errors in audio or video transmissions may be tolerable, but when we transfer text, we expect a very high level of accuracy.
We design digital systems to be resistant to noise by abstracting precise voltages to be ones and zeros. Unfortunately, errors still occur during data transmission of many bits, so that one of these bits or more might get flipped, so the ones become zeros and the zeros become ones. The more bits we send, the higher chance that one of our bits will get flipped. To understand how we detect and correct these bit flip errors, let's start by discussing a concept called the Hamming distance. The Hamming distance between two code words is the number of bits that are different between two valid code words. The Hamming distance of a code as a whole is the minimum Hamming distance between all code words. Suppose that we want to send just one bit between two components. The Hamming distance between these code words is 1, as only one bit is different between these two code words. Since these two code words are the only words in the code, the distance of the code is also 1. When the Hamming distance of the code is 1, the receiving component can never detect an error, because if a bit flips, the receiving component still receives valid information. Let's change our code so that it still has two code words. But now, each code word consists of 2 bits. We would still have our 2 valid code words, but the Hamming distance for this code would be 2 because each code word differs from the other by 2 bits. In this situation, there are 2 potential bit encodings that would be considered invalid. If one bit gets flipped in error, the receiving component would know that an error occurred because the message does not match valid information in the code. However, the receiving component cannot correct the error because the error has an equal Hamming distance from both valid code words. If we add one more bit, we would have 2 valid code words whose Hamming distance would be 3. We would also have 6 invalid code words. In this situation, the receiving component could still detect if an error occurred in one bit. But now, because the erroneous word has a Hamming distance of 1 from one valid code word that is less than the distance of 2 from the other, we can correct the error. Let's add one more valid code word to our code. If we simply add a code word at this vertex, the overall distance of our code is reduced to 1 from 3 because the minimum distance between these 2 code words is 1. It is irrelevant that this code word is distance 2 from this one, or that this code word is distance 3 from that one. Because we cannot detect every 1-bit error, we say that this code can neither detect nor correct 1 bit of error. However, with a better design of our code, we can create a similar code that would be able to encode 3 valid code words that all have a Hamming distance of 2. This code could detect an error in one bit, but it could not correct any errors.
Now we will learn about the different types of errors. Whenever bits flow from one point to another, they are subject to unpredictable changes because of interference. This interference can change the shape of a signal. In a single bit error, a 0 is changed from a 1 to 0. Single bit error. The term single bit error means that only one bit of a given data unit is changed from 1 to 0 or from 0 to 1. In a single bit error, only one bit in the data unit has changed. It shows the effect of a single bit error on a data unit. To understand the impact of the change, imagine that each group of 8 bits is an ASCII character with the 0 bit added to the left. Burst error. The term burst error means that 2 or more bits in the data unit have changed from 1 to 0 or from 0 to 1. It shows the effect of a burst error on a data unit. A burst error is more likely to occur than a single bit error. The duration of noise is normally longer than the duration of one bit, which means that when noise affects data, it affects a set of bits. The number of bits affected depends on the data rate and duration of noise. Redundancy. The central concept in detecting or correcting errors is redundancy. To be able to detect or correct errors, we need to send some extra bits with our data. These redundant bits are added by the sender and removed by the receiver. Their presence allows the receiver to detect or correct corrupted bits. Detection versus correction. The correction of errors is more difficult than detection. In error detection, we are only looking to see if any error has occurred. The answer is a simple yes or no. We are not even interested in the number of errors. A single bit error is the same for us as a burst error. Forward error correction versus retransmission. There are 2 main methods of error correction. Forward error correction is the process in which the receiver tries to guess the message by using redundant bits. This is possible, as we see later, if the number of errors is small. Correction by retransmission is a technique in which the receiver detects the occurrence of an error and asks the sender to resend the message. Coding. Redundancy is achieved through various coding schemes. The sender adds redundant bits through a process that creates a relationship between the redundant bits and the actual data bits. The receiver checks the relationships between the 2 sets of bits to detect or correct the errors. The ratio of redundant bits to the data bits and the robustness of the process are important factors in any coding scheme. Modular arithmetic. A basic concept to computer science in general and to error detection and correction in particular is modular arithmetic. Modulo 2 arithmetic. Of particular interest is modulo 2 arithmetic. In this arithmetic, the modulus n is 2. We can use only 0 and 1. Operations in this arithmetic are very simple. Other modulo arithmetic. We also use modulo n arithmetic through the book. The principle is the same. We use numbers between 0 and n to 1. If the modulus is not 2, addition and subtraction are distinct. If we get a negative result, we add enough multiples of n to make it positive. Let's now talk about block coding. In block coding, we divide our message into blocks, each of k bits, called data words. We add r redundant bits to each block to make the length n equals k plus r. The resulting n-bit blocks are called code words. How the extra r bits is chosen or calculated we will discuss later. For the moment, it's important to know that we have a set of data words, each of size k, and a set of code words of size n. Error detection. An error detecting code can detect only the types of errors for which it's designed. Other types of errors may remain undetected. If the following two conditions are met, the receiver can detect a change in the original code word. The receiver has a list of valid code words. The original code word has changed to an invalid one. Error correction. Error correction is much more difficult than error detection. In error detection, the receiver needs to know only that the received code word is invalid. In error correction, the receiver needs to find the original code word sent. We can say that we need more redundant bits for error correction than for error detection. We can see that the idea is the same as error detection, but the checker functions are much more complex. Hamming distance. One of the central concepts in coding for error control is the idea of the Hamming distance. The Hamming distance between two words is the number of differences between the corresponding bits. We show the Hamming distance between two words, x and y, as d parentheses x, y. The Hamming distance between two words is the number of differences between corresponding bits. Minimum Hamming distance. Although the concept of the Hamming distance is the central point in dealing with error detection and correction codes, the measurement that's used for designing a code is the minimum Hamming distance. In a set of words, the minimum Hamming distance is the smallest Hamming distance between all possible pairs. We use dmin to define the minimum Hamming distance in a coding scheme. To find this value, we find the Hamming distances between all words and select the smallest one. 3 parameters. Before we continue with our discussion, we need to mention that any coding scheme needs to have at least 3 parameters: the code word size n, the data word size k, and the minimum Hamming distance dmin. A coding scheme C is written as C parentheses nk, with a separate expression for dmin. Hamming distance and error. Before we explore the criteria for error detection or correction, let's discuss the relationship between the Hamming distance and errors occurring during transmission. When a code word is corrupted during transmission, the Hamming distance between the sent and the received code words is the number of bits affected by the error.
To understand how we correct and detect errors, let's start by discussing a concept called the Hamming distance. The Hamming distance between two code words is the number of bits that are different between two valid code words. The Hamming distance of a code as a whole is the minimum Hamming distance between all code words. Suppose that we want to send just one bit between two components. The Hamming distance between these code words is 1, as only one bit is different between these two code words. Since these two code words are the only words in the code, the distance of the code is also 1. When the Hamming distance of the code is 1, the receiving component can never detect an error, because if a bit changes, the receiving component will still receive a valid piece of information. Let's change our code so that it still has 2 code words, but now each code word consists of 2 bits. We would still have 2 valid code words, but the Hamming distance for this code would be 2 because each code word differs by 2 bits. In this situation, there are 2 potential bit encodings that would be invalid. If an error with 1 bit occurs, the receiving component would know that an error occurred because the received message does not match valid information. However, the receiving component could not correct the error because the error has an equal Hamming distance from both valid code words. If we add one more bit, we would have two valid code words whose Hamming distance would be 3, and a code with Hamming distance 3. We would also have 6 invalid code words. In this situation, the receiving component could still detect if an error occurred in one bit. But now, because the erroneous word has a Hamming distance from one valid code word that is less than the distance from the other, we can correct the error. Let's add one more valid code word to our code. If we simply add a code word at this vertex, the overall distance of our code is 1, because the minimum distance between any two code words is 1. It is irrelevant that this code word here is distance 2 from this one, or that this code word is distance 3 from this one. This code can neither detect nor correct an error reliably, because the Hamming distance of the code is determined by the minimum distance, which is 1. However, if we are creative, we can create a similar code that can encode 3 valid code words that all have a Hamming distance of 2. This code would have an overall Hamming distance of 2 and can correct an error in 1 bit. Unfortunately, it cannot correct any errors. Now, how do we intelligently increase the distance between two code words so that we can detect errors? Naively, we could increase the distance by sending a message multiple times. The receiving component would detect the error by simply comparing the two sets of bits. However, this method is ineffective, and it requires a lot more hardware and would become expensive very quickly. Alternatively, we could require that the transmitting component send an even or odd number of 1 in its transmission. In this case, we would simply add one more bit to the transmission, and we would set this bit to be a 1 or a 0, depending on the number of 1s in the original transmission. If we want an odd number of 1s for the transmission, we would add a 0. The strategic addition of a parity bit in a code can increase the Hamming distance of the whole code by 1 and enables to detect and potentially correct more errors.
Minimum distance for error detection. Now let's find the minimum Hamming distance in a code if we want to be able to detect up to S errors. If S errors occur during transmission, the Hamming distance between the sent code word and received code word is S. If our code is to detect up to S errors, the minimum distance between the valid codes must be S plus 1, so that the received code word does not match a valid code word. Minimum distance for error correction. Error correction is more complex than error detection. A decision is involved. When a received code word is not a valid code word, the receiver needs to decide which valid code word was actually sent. The decision is based on the concept of territory, an exclusive area surrounding the code word. Each valid code word has its own territory. We use a geometric approach to define each territory. Now we will learn about linear block codes. Almost all block codes used today belong to a subset called linear block codes. The use of nonlinear block codes for error detection and correction is not as widespread because their structure makes theoretical analysis and implementation difficult. We therefore concentrate on linear block codes. In a linear block code, the exclusive OR or XOR of any two valid code words creates another valid code word. Minimum distance for linear block codes. It's simple to find the minimum Hamming distance for a linear block code. The minimum Hamming distance is the number of 1s in the non-zero valid code word with the smallest number of 1s. Some linear block codes. These codes are trivial because we can easily find the encoding and decoding algorithms and check their performances. Simple parity check code. The most familiar error-detecting code is the simple parity check code. In this code, a k-bit data word is changed to an n-bit code word, where n equals k plus 1. The extra bit, called the parity bit, is selected to make the total number of ones in the code word even. Although some implementations specify an odd number of ones, we discuss the even case. Hamming codes. Now let's discuss a category of error-correcting codes called Hamming codes. These were originally designed with dmin equals 3, which means that they can detect up to 2 errors or correct one single error. Although there are some Hamming codes that can correct more than one error, our discussion focuses on the single-bit error-correcting code. Now in the end, let us summarize what we have learned in this lecture. The term single-bit error means that only one bit of a given data unit, such as a byte, character, or packet, is changed from 1 to 0 or from 0 to 1. The central concept in detecting or correcting errors is redundancy. To be able to detect or correct errors, we need to send some extra bits with our data. The correction of errors is more difficult than detection. In error detection, we are looking only to see if an error has occurred. Redundancy is achieved through various coding schemes. The sender adds redundant bits through a process that creates a relationship between the redundant bits and the actual data bits. In block coding, we divide our message into blocks, each of which are k-bits, called data words. We add r redundant bits to each block to make the length n equals k plus r.